The center of mass system. A collection of two or more bodies is called a system. And any force on the bodies inside the system from bodies outside the system is called an external force. The forces between two bodies inside the system is called an internal force. Sigma F internal force equal to 0. Because forces appears in pairs. Action force and reaction force inside the body is always equal in magnitude and object interaction, but they never cancel out because they act on different bodies. Now we want to put all forces inside the system together. Definitely it will involve these two forces, and the sum of these forces is 0. So all sigma F internal force is 0. A special point. Every body has a special point called the center of mass. You look at this, a baseball bat. You throw the baseball bat, it turns around, but you look at a special point called the center of mass. It moves like a single particle, right? The center of mass of a body or a system of bodies is the point that moves as though all the mass were concentrated there and all external forces were applied there. Center of mass. We start with a system of a few particles, and then we consider a system of a great many particles. System of particles. Figure shows two particles of mass m1 and m2 separated by a distance d. We choose the x-axis overlapping with the line which connect the particles m1 and m2. x1 and x2 are their positions respectively. We define the position of the center of mass of this two particle system to be x center of mass equal to m1x1 plus m2x2 over m1 plus m2. Well, for the future, we will rewrite this one as sigma mi xi. This is sigma mi. Okay, so in this case, we could extend to many points. Okay. And sigma mi is the total mass of this system. I'll replace it with m. Okay. In three-dimensional, we're similar. X-com, Y-com, Z-com has similar formula. Okay. S-com equal to sigma mi xi over big M. Y, we replace xm with y-com. Okay, this was yi, so it become y-com equals sigma mi yi m. I is the particle number I. Okay. Similar, z-com equal to sigma mi zi over m. What we do, so in a system, the number I, the particle number I, its location is Ri, Xii, Yij, and Zik, where I can be 1, 2, 3, 4, 5, up to many. And the center of mass, the location is R. It has three components, X, I, Y, J, Z, K. We based on above definition. We have x equal to sigma mi Ri over sigma mi. And the sigma mi equal to the total mass of the system. So we have this one. And furthermore, if it is not separate masses, it's a solid body. We cannot separate one mass to another mass. So we change this mi as dm, very small mark, and the sigma become integration. So above equation becomes r com equal to integration r mr divided by the m, where m is this total mass dm integration. And this we write it in 3 components. We get com is this one, ri is this one. We find this one. We compare the ijk, the coefficient in front of the ijk. We get x com equal to integration x dm of m, y com equal to integration y dm of m, z com equal to integration z dm over m, where m is the total mass equal to integration of dm. Now let me explain to you how I remember this formula. This is a basic formula. X com equal to sigma mi xi over sigma mi. From this formula, we could extend to y com, z com. We can extend to integration dm and so on. How do I remember this formula? I just write equation. Sigma mi xi equal to sigma mi xi. I move this xi out. Or inside is 1, 2, 3, 4. Out, you don't have a sigma. So I change this one as a x com. You see that's x com equal to sigma mi xi over sigma i. Exactly the same thing. All right? So, and then we extend to the integration. Okay, integration. This is equal to, this is the integration, m replaced by dm, x, and the sigma mi is big M. That's it. Now, important thing is, the position of the center of the mass of an object does not depend on the reference frame from which it is calculated. Okay? So you can find a good one, make things much easier. Okay? It's nothing to do with the frame. And this definition has been proved by experiments. Why this one? Has been proved by experiment. You can bypass one or more of these integrals. If an object has a point, a line, or a plane of symmetry, the center of mass such an object then lies at that point, on that line, or in that plane. For example, the center of mass of a homogeneous sphere, which has a point of symmetry, is the center of the sphere. The center of mass of a homogeneous cone, whose axis is a line of symmetry, lies on the axis of the cone. The center of mass of an object need not lie within the object. For example, you have a donut, okay, and the center mass doesn't have another dot. Yeah. Horseshoe, the center of mass of horseshoe does not have an eye. Okay. If the object has uniform density rho or mass per unit volume, that is, its density rho is the same for all given element of the object as for the whole object, then we can write the density equal mass over volume. Okay. The small one is dm over dv. The big one whole as m over v. If it's a uniform, they are equal. Okay. Then we can write this one. By definition, x com equal to x dm integration over m. This dm is rho dv. This big M is rho v. Okay, where rho dv is the dm. Rho v is the big M. Also, same for the y com, the z com. Here we see rho in numerator, rho in denominator. They are the same. so we cancel out. Same thing for y and z. We can use this integration to find x com, y com, z com.
Is there a simple way to locate the center of mass of an irregular flat object? We'll hang the sheet from a support point near its edge. Since it is in stable equilibrium, we know that its center of mass is directly below the point of support. A plumb bob is hung from the same support point, and we snap the chalk-filled string to put a line on the sheet. Then we repeat the same action from another point of support. Since the center of mass must be located on both these lines, it must be at their intersection. If we suspend the sheet from the intersection point, it is stable in any orientation. This animation shows the forces acting on the sheet and the net restoring force that results when the center of mass is not below the point of support. We'll use this air table to demonstrate the motion of an object's center of mass. A flat piece of acrylic has been weighted on one side so that the center of mass is located beneath this orange spot. To show that the center of mass is located at the spot, we can balance it on a finger at that point. Now the acrylic is placed on the air table and given a push. The acrylic and the weight move in circles, but the center of mass moves in straight lines.
Sample. 3 particles of mass M1, 1.2 kilogram, M2, 2.5 kilogram, and M3, 3.4 kilogram, form an equilateral triangle of each length 140 cm, where in the center of mass of these 3 particle system. Sample. 3 particles of mass M1, 1.2 kilogram, M2, 2.5 kilogram, and M3, 3.4 kilogram, form an equilateral triangle of each length 140 cm, where in the center of mass of this 3 particle system. We run all the information. M1, mass 1.2 kilogram, X1 0, Y1 0, M2 2.5 kilogram, X2 140, Y2 0, X3 is the middle, so mass is 3.4 kilogram, X3 is half, 170. Y3 we can calculate from this triangle is 121. Then we put the formula. X com equals sigma M1 X1 plus M2 X2 plus M3 X3 divided by the total mass M1 plus M2 M3 equal to 33 cm. Y com is equal to sigma M1 Y1 plus M2 Y2 plus M3 Y3 divided by man. 3 put together, we get a 3. So we get the answer. Total mass 7.1 kilogram. X-com is 83 cm here. Okay. Y-com 58. So this is the center mass of this triangle. Sample. Figure shows a uniform metal plate P, this is a P, of radius 2r, which a disk of radius r has been sampled out, removed in the assembly line. Using the XY coordinates system show, this is X, this is Y, locate the center of mass com of this piece's plate. Now in this case we find if we put one piece here, okay, then we get this one. This one is just use the center of mass is here, okay. Now this piece, look at above the x-axis and below the x-axis, they are symmetry. So you have a symmetry, we know the center of mass must be located on the x-axis. That means yp equals 0, How about the x? And we see, we took these two pieces as two particles. This particle mass, I know this one. The center mass is located minus r, right? Yeah. And this one, the location is what I want to find. So let's see this. We put it together. Where is the center mass? Here, 0, right? And by definition, this two pieces, it should be x1, m1, x1 plus m2, x2, divided by m1 plus m2. Here we call this one the small pieces. This is the p. This must be 0. Why? Because I take reference here. This is 0 at here point. Then we see numerator must be 0. I get ms xx plus mp xp equal to 0. Okay? So xp, the location where I want to find is minus mx ms of z. Let me write all these one. Ms is the mass is the area, pi r squared, multiplied by a thickness, t. This is the volume. Volume multiplied by density is mass. And MP is two pieces, big one minus smaller one. Big one is pi 2r squared. Small one is pi r squared. This is the area. We multiply by thickness t, this is the volume. And then multiply by the density, it is the mass. And this is about 3 pi r squared t rho. And excess minus r. We put these 3 inside, we get xp. Xp about 1/3 I is here. The plot is a little bit wrong. It should be 1/3.